Folks, we'll be getting started promptly here at 11:30 Eastern. Here we go. All right. Good morning, everyone. My name is Mark Jones, hailing from a very warm Atlanta, Georgia this morning at a company called Georgia Educational Solutions. We have been in business here since 2010 and representing a fantastic e-learning product for automotive technology and now heavy vehicle called Electude. And so I am very pleased to say that I've got a great friend and colleague with me by the name of Mr. Darcy Wedel. And Darcy hails from Great Bend, Kansas, somewhere out there in the Midwest. I promise someday I'm going to come out and see him. I hear it's a beautiful place. We really thank you for joining us this morning. This is session 3 of 6 for me this week. So this is going to be a very interesting week. I have 3 back-to-back today. We're starting with Electude and their engine management simulator. From there, we'll be going into a new product for me called SkillVary that deals with virtual spray painting and virtual welding. That's at 12:30 Eastern Standard Time. And then later today at 2:30 to wrap things up, Miss Michaela Alpers from Career Team is going to be giving you a preview of a fantastic new partner product with Electude called Career Edge. And that deals with soft skills and employability. So to get started here, what I'd like to do, I'm sharing my screen, hopefully everyone can see that. I'll be monitoring the chat today. We've put up about 3 or 4 polling questions. We would greatly appreciate your feedback on the polling as well. Unfortunately, for anyone that was requesting a closed caption session, we were not able to get that running in the time that we have, so I deeply apologize for that. We struggled with it. I sent email to CTE support, but did not get a response yet on how to enable closed captioning. So my apologies on that. We'll try to get that straightened out for you. I thought I would start out with a quick, short, sharp video. It's a very timely moment to play this for you. It's on Electude's main page, and I'd like to go ahead and play that. And it's just about a minute long or so, and then quickly run down the products, and then I'm going to turn it over right to Darcy, and he'll spend the rest of our session in the engine management simulator. So here we go. Hopefully you all can hear this.
Shut down the world. It distanced students and teachers. It emptied our shops. Nothing will be the same. Now, as we slowly get back to work, everything has changed. Students who have fallen behind need to get back on track while staying safe from the virus. Instructors need to prepare for a world where students may be on campus only part-time. They need a comprehensive and flexible solution for whatever comes their way. With Electude, learning happens in any setting, whether students are in school or at home. Electude's theoretical and practical e-learning solutions empower instructors to get the maximum potential out of their students. As you prepare for this new educational reality, make Electude your plan A and your plan B. Lecture, assign lessons, and capture test results real-time safely from home. Electude has the webinars, tutorials, and direct support you need to get up and teaching fast and easy. Join the thousands of schools that use Electude for the online and in-class instruction. Get started at electude.com and let potential fly.
All right, I appreciate you all looking at that for just a moment. I'd like to quickly run down their product solutions just as a brief introduction. And here they are. In light vehicle, we have automotive essentials. This is Electude's crown jewel. This is what you would be using in the classroom. And I'm going to share several sites along the top of my browser bar here in a minute on some fantastic customers right in the state of Tennessee. So automotive essentials would be the primary product. They do a great job with new BEV and HEV electric vehicle or electric drive. Darcy is going to be introducing you to the most sophisticated engine management simulator anywhere on the market, we believe today. Just a fantastic product there. And then quickly coming down the home stretch here, I want to identify some partner product solutions. Part of Electude's new ecosystem. Bob McGinn will be with us tomorrow morning at 8:30 Eastern time to introduce C-CAR technology. I believe that's Eastern. We'll check that. And that's your new safety content with COVID-19 content tomorrow morning. We have vehicle repair and diagnostic software from MotoLogic. We have Haynes All Access manuals. Consulab training aids has stepped up with the hardware arm. So we can now integrate e-learning content from a distance with some fantastic hardware training. And then down at the very bottom, last but not least, there is Career Team and Career Edge. And then just to cap it off here are some of your districts locally that I'm sure you're going to be familiar with. We'll go over to Bledsoe County High School. I should get rid of the attendee window there, sorry. And then on to Cookeville High School. If I can get my mouse going there, there we go. So there's Cookeville. We've got Glencliff, that's with Larry Molstat up in Metro Nashville. Some great guys down at Jefferson County High School there. Lebanon High School, Allen Davis, just to your east of Nashville. In Wilson County, Oakland High School with Mr. Philip Vining, part of the Rutherford County group. Volunteer High School, as well as Union County High School. So all those folks run Electude. There would be some great references for you in the future just to find out how things are going. So at this time, I'd like to go ahead and unshare my screen and go ahead and Darcy, without any further ado, you've got the ball.
All right. Okay. Well, welcome everybody. And Mark, thanks for that great introduction. And we'll go ahead and jump right into teaching diagnostics from a distance. So Mark, can you see my screen? Just want to confirm that. Okay, yes. Fantastic. Okay. Yeah, so just a little bit of background about myself. So I'm a former technician. So I worked in a General Motors shop for about 10 years through the 90s. And then through most of the 2000s, I was a teacher. I taught automotive at Barton Community College here in Kansas. And so, you know, in about 2008 or so, I stumbled upon this program called Electude and started using it with my students. And, you know, one thing kind of led to the next. You know, I drank the Kool-Aid and now I work for the company. So since about 2012, I've worked for Electude full-time. And I enjoy going to conferences and presenting, although I must say that presenting, you know, via Zoom, it's getting to be second nature now, but as probably many of you have also experienced, it's a little bit different, and not seeing live faces in front of you, not being able to kind of work the crowd a little bit and see what's resonating, what's not. But we all kind of get used to that, and I know many of you will be teaching from a distance this fall. And so the whole, what I'm wanting to accomplish here today is not just show you Electude, but I want to give you some tips, maybe a couple, if you can pull maybe one or two things away from this presentation that you can implement right away in your automotive training program that helps you teach students, whether or not you have Electude or not. That's my goal here today. And so we'll go ahead and just jump right in. As you think about those questions and things like that, write them down or put them in the chat button there. I will from time to time maybe pause and see if there's any questions. So Mark is going to be monitoring that chat box. So through this presentation, I'm going to be kind of playing the role, if you want to think of it that way, as a teacher, and the participants, you all will be somewhat of the students. But I want you to be thinking, you know, put yourself in my place and how you might do something similar with your students this fall. So without further delay here, let's jump right on in here to our presentation. We'll go to my next slide. There we go. So let's go back about 30 years, I guess. And when I was a young student attending vocational classes back in 1990, 1991, this was the technology of the day. And when I was going to school, this is what the vehicle they were preparing me to work on. And for those of you that have ever had the pleasure of working on these cars, I kind of call them the modern day Model T. I just think these vehicles and this engine was so simple to work on. You know, you could just do about anything on this car in 2 hours or under. I mean, you know, and we didn't need a lab scope back in those days. If you had a misfire, you either had carbon track plugs or you needed a new ignition coil pack. That was one of those two things. If the car come in your bay with making a growling noise, it either had a bad water pump or an alternator or both, you know, but, you know, it was a very simple car to work on. And you think about how things have changed since this car here, you know, and, you know, this car didn't have ABS. It didn't have, you know, any type of CAN bus system. You know, it obviously had a computer and fuel injection, but no OBD2. It was a very, very simple car. But so here we are today, and think about the vehicles maybe that are in your shop that you're using to train your students for today's current technology. But think about how rapidly things are changing. You know, obviously a ton has changed in the last 30 years, but even the last 5 years, think about how much has changed. And now we're entering the world of driver assist technology and things like that. In another 30 years, it's very conceivable if there won't even be a steering wheel in that car, or brake pedals or accelerator pedals. You'll sit down in there, click a button, and off we go. So how are we to train today's students for not only working on the cars of today, but help prepare them for working on the cars of tomorrow? How can we set them up for success today to work on technology that doesn't even exist yet? And that's kind of where I think, especially teaching from a distance now, you know, we can focus on a couple of very basic concepts that are true, no matter if you're talking about a Model T Ford, a 1990 Buick LeSabre, a 2015 Ford F-150, or maybe a 2035 Tesla, who knows what. There's a common thread that's the same through all of these vehicles, and I think will continue for as long as we drive cars. These things don't change all that much, but we're going to have wires that carry current and wires that carry data. And at least, you know, even going back to the 1990 Buick LeSabre there, we had wires that carried current, wires that carried data. And I believe every car from here on out, these are the two types of circuits we have. And if you think about this, every wire going in or out of that computer is one of these two types of circuits. And for me, that really simplifies things quite a bit. And now, I didn't always come from this mindset. And if you've been teaching for a while, and if your program is ASE certified, you can probably rattle off about maybe 50 or more tasks in the area of electrical testing, where, you know, students have to diagnose a windshield wiper circuit, diagnose a door lock, diagnose a seat, diagnose a window motor, and diagnose this, diagnose that. And I think, at least I fell into this trap a little bit when I was teaching, is we focus so much on completing those tasks, we sometimes fail to realize how confusing that is to students. And they think, oh my gosh, how am I ever going to get to the level of where my teacher is? Because, man, one day I could be diagnosing a door lock, the next car coming in could be a windshield wiper, you know, whatever. Or maybe a driverless technology thing. How in the world am I going to learn all these diagnostic procedures? And, you know, and then oftentimes the students, they lack confidence, and then they go choose another career path. So I think in some ways, the long ASE task list that we have, I know they're well intended, because, you know, it is important to expose the students to all these things, but if we focus on those things too much, and, you know, I think students kind of get lost in it, and they lack then that confidence to go out there and do it. But going forward, I think if we can make it simple like this, students, you don't have to worry about how to diagnose a windshield wiper or a seat motor or a door lock. They're all diagnosed in the same way, because there's only two types of circuits on the car. you've got a wire that carries current or a wire that carries data. Those are the only two types of circuits there are. And you need to know what tools and testing methods to follow when you're working on a wire that carries current versus a wire that carries data. And if we can break it down, and especially during this time where we have teaching from a distance, focus on these two things, forget about all those other things. Let's ingrain in our students how to do these few tests, and then you're going to be setting them up for a lifelong opportunity and success, because they understand electrical and testing and that sort of thing. So if we go on here to my next slide, let's talk about what tools you can use to diagnose wires that carry current. Obviously, we can use a test light. You know, we've that's been a staple in the technician's arsenal of diagnostic tools for many years. Test light works great to diagnose wires that carry current. However, this is not a good tool to diagnose wires that carry data. A voltmeter. Obviously, we can do a voltage drop test on a ground wire, like to the fuel pump, and you can, or even the starter motor, for example, and you can easily identify high resistance in wires and cables by doing a voltage drop test. However, although we do use a voltmeter for diagnosing wires that carry data, you're not going to use that voltmeter to do a voltage drop test on a CAN bus wire. There is no significant current flow in a wire that carries data, so you're not going to have a voltage drop reading there. So that type of test is useless on a wire that carries data. An ohm meter, however, is very useful for example, measuring the resistance of the terminating resistors on a CAN bus system, or checking for continuity on a data bus system. But an ohm meter is practically useless on diagnosing a wire that carries current. No technician is going to put, unhook the battery and measure the resistance from the negative, from the positive cable of the battery to the starter connection. I mean, that wire could be, or that cable could be totally corroded and hanging on by just one thread, and it's going to measure low resistance. So ohm meters we don't use to diagnose wires that carry current. Obviously, a lab scope and a scan tool are going to be very useful in either scenario, but just some of the tools that we use. And so I think when a student has a problem with an electrical circuit, they first need to identify what type of circuit it is. Is it carrying current or is it carrying data? And then what tools can I use to help me find the problem? So moving on here, what we're going to do is we're going to actually practice some of these things, and we'll kind of continue this thread of discussion, wires that carry current, wires that carry data. And we're going to use the Electude simulator to demonstrate, these diagnostic practices. So what we're going to do here next is kind of transition a little bit away from here. And we're going to basically open up the garage door here, and with Mark's help, we'll push this car in and see what we got here today. So now I'm going to be kind of playing the role of the teacher and kind of modeling maybe how you could use a tool such as this in a web Zoom meeting with your students. So we're going to go ahead and start this thing up. And here's the car we're working on today. And here's our work order. It says vehicle towed to the shop, engine cranks but does not start, diagnose and repair as needed. Okay, so there's our task before us. And so maybe, let's maybe mention here for a little bit, I'm a former teacher. I appreciated when cars would come in broken and I could get my whole class around that car. I had a projector and a screen. I even had a smart board out there in the shop where I could project lab scope images on and things like that and draw on over things. And, nothing beats real hands-on training with your students. But oftentimes, trying to show students how to do various tests on a real car where everybody's kind of standing around it, it's extremely difficult. And obviously now, with the COVID thing, going on. You're not having those face-to-face encounters as much as you had in the past. So when it comes to teaching concepts, diagnostic techniques, and so forth, when you're using a simulator such as this, I mean, everybody can see. I can do probably a half dozen tests in a shorter amount of time than it would take in the real world just to gather the equipment and get it all set out on the bench. So there are some extreme advantages, which you'll see here, as using a simulation type product to teach concepts. No one is trying to replace the actual experience of back probing a terminal with a back probe pin, or taking off a sensor, replacing a wire, that sort of thing. But just like an airline pilot practices hundreds and thousands of hours in a simulator, honing their skills, with products such as this, we can really ingrain in our students through repetitive practice every day, over and over and over again, until they get that diagnostic strategy down pat. So if this is our car, crank no start, and we're teaching a diagnostic flow or strategy, what might, and here again, you're welcome to type suggestions in, and Mark, you can break in if anybody has a comment, by the way, okay? Just feel free to interrupt me. But what should we do here first? Do we check for bulletins? Do we scan the vehicle? What should we do here first? And I think if I could, I'm guessing that probably many of you are thinking, or maybe writing down, hey, we need to verify the concern. So let's do that here first. We'll crank the old car over and see what we got here. And just make some observations as I'm cranking this. So I don't know how well the volume's coming through, but it is cranking at a decent speed. It sounds like the engine's got compression. The check engine light is coming on, but look at the RPM. There is no RPM fluctuation there on that tack at all. That's just an interesting observation. But yeah, definitely not starting here. It doesn't seem like we're getting any fire or whatnot. So what do we do next here? Some might say, well, let's do just a real quick visual inspection. So yeah, I agree with that. Let's just see if there's any evidence of maybe rodent damage, loose battery connections and things like that. We don't want to spend a lot of time here, but let's say 30 seconds just looking the car over. Everything kind of looks good here. No visible problems. So what next? Do we do a bulletin search, or do we check for codes? Personally, I like to check for codes before I do a bulletin search, because oftentimes those bulletins have trouble codes associated with them. And I once had a teacher tell me I like to do my diagnostics in the seat of the car with the air conditioner on, if possible. Of course, in this case, we can't turn the air conditioner on, but we can definitely check for codes here. So let's see what we have. We'll identify the vehicle. We are getting a VIN number there. Systems, engine management. Let's see what we got here for fault codes. Keys on. Uh-oh. ECU, communication not possible. TCM, that's throttle control module, communication not possible. So let's just make sure here with that. We'll just maybe pick a couple data things here. Display selection. Yeah, indeed. There's I'm not getting any data, nothing. It's like the computer is dead. We're not communicating with the ECU at all here. And that makes sense. We weren't seeing RPM going here either. So we got definitely something going on here with communications, or maybe some power going to the computer or something like that. So I guess this diagnostic tester isn't going to do us too much good for now, so we're going to put that away. I'll tell you just a little bit about this car, some things on it. So here's the ECU, or the PCM, for the engine management system. We've got coilover plug ignition. which most of you are familiar with already. A multi-port injection. So this cart doesn't have direct injection. It's got your MPI system there. We've got an inductive type crank sensor, a Hall effect cam sensor over here, an analog mass airflow sensor, 3-wire, EGR valve, canister purge, 2-wire canister purge valve there, oxygen sensor. It is a heated narrow band oxygen sensor, temperature sensor, air temp sensor. Here's our, down here is our throttle control motor and controller. So this is a throttle by wire system. And that's kind of, oh, and of course our relays and our fuses and powers are over here. This connection, this goes to underneath the dash to the pedal position sensor. So this is how we would access measuring voltage at the pedal position sensor if we need to do that here in a bit. But all these parts and pieces are removable. And in fact, the system is tracking us right now. Every click, everything that I'm doing right now in this program is being tracked and monitored and will later be reported. So and that's another important thing. You know, if you're teaching from a distance, how do you know if your students are actually doing the work? So you can't physically be there to watch them. So let's, where do we want to go here? Yeah, let's maybe, you know, we'll maybe do another visual inspection. Everything looks good there. We check for bulletins, no bulletins whatsoever for loss of communication. So where do we go? You know, what's the next step? Where would we tell our students to go here next? Well, no communication with this. Obviously, it could be a bad computer, but I don't think any of us are ready to condemn the computer at this point. We probably need to check to make sure, you know, start with what's simple, powers and grounds, right? So let's get up the wiring diagram out here and we'll take a look here, what we got here on the old wiring diagram. So, so here's our main power relays over here. So here's our ECU. Our main power feed is from fused F6. So this is our main power wire, supplies all the power to the ECU. And then over here are the grounds, pin 3 and 37. You might notice over here at these relays, there appear to be from these switches, a wire coming in here to pin 4. From this fuse, there's a pin 7. From this fuse, there's a pin 6. There's this K1 relay's also got power coming. It looks like it's got power coming here. What are your thoughts and ideas on this? Have you ever seen a computer have that many power wires coming into it? 1, 2, 3, 4, 5 power wires coming in. Does that make sense? No, it doesn't make sense, does it? So these wires here are sensor wires. So if you can imagine on the inside of the computer having a little high resistance or high impedance resistor in here. Imagine, and this, you know, sometimes students ask, why do I need to know Ohm's law? What does that do for me? Well, here's a good example of why you need to understand Ohm's law. Inside this computer, there's a little resistor. And across that resistor, the computer's measuring voltage drop. So if it's a high impedance resistor, that means there's just going to be a tiny trickle of current going through this wire. There's no significant power being run through this wire. But when this switch closes up here, power flows through the injectors, obviously, and that's the most important thing. But this little voltmeter in the computer measures then a voltage drop across there, and the computer then knows that this switch is closed. So if the computer doesn't measure a voltage drop, then this relay never closed. And then the computer then can set a trouble code for the K2 relay not closing. Same way here on pin 7. There's a little resistor in here, and the computer is measuring voltage drop. So these are signal wires going into the computer that tell the computer whether or not these relays are functioning. Or maybe even if we have a blown fuse, that would cause that problem as well. So With that explained, let's go over here and pin 26, 3, and 37. We need to check those circuits. So let's pull our wiring diagram out of the way here a little bit. Now, obviously, back probing here at this computer is going to be extremely difficult with this connector. So thankfully here we have a breakout box. And if your students go and work for a dealership somewhere, they're going to have access to breakout boxes. And so, we got the same thing here. So we're going to turn the key off. And just to make sure, we're going to follow safe procedures. We should never unplug the ECU with the battery connected. So we're going to unplug the battery, go over here, unplug the computer, and now we'll hook up our breakout box. Hook our battery back up. So you can see even how much more efficient this is for training purposes. For us to do that on a real car, that might have taken 20 minutes to do just what I did there, to connect that breakout box, unhook and unhook the battery. All that is valuable time wasted if you're just trying to demonstrate a point here. So if we look here now, every pin on the shown here in the computer, 26, 3, and 37, those match our pins here on the breakout box, which is nice and handy. So we're going to grab our multimeter. We got a manual range meter, and let's see here. We're going to put this on one of the ground wires, 3 and 37. Let's check that first. And then the power wire is 26, right? Yeah, 26. We'll put our red lead on 26. And I always like to ask students, okay, before we make this connection, what do you expect to see? And I think that's a very important diagnostic question. Oftentimes is neglected, especially if a technician's following a flow chart and a manual. They just, it's very easy to kind of get lazy with those flow charts and just, you got voltage here, you got voltage there, yes, no, da, 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 da. But what do you expect to see? And so obviously we want to expect to see battery voltage here. And when we turn the key to run, so let's do that. Let's see if we got battery voltage. Oh, on the wrong wire there. So there we go. There's what I expect to see, 12 volts. And let's go ahead and check, we'll make sure we got continent path to ground on 37. We'll move this one from 3 to 37. Yeah, we got battery voltage there. Maybe you want to check a voltage drop here, so we can do that as well. We can put the red lead here on 37 and put this lead here on the negative battery and put the key on. We should have, I'll put this on millivolts here. We should have a very low voltage, yeah. So no significant voltage drop on that one. Let's check that other one. That's 3. Make sure we don't have a voltage drop there. Want to see under 100 millivolts or 100 millivolts, so that's good. That's good. Let's do a power wire. Let's make sure there's no voltage loss on the power side. Just to be double sure. Let's do this here. I'll put this on 26. This one on the positive post of the battery, and we'll see if there's any voltage loss on the positive side. Nah, nothing really significant there at all. Okay, so I think we've determined that, hey, the computer's got voltage. It's got ground, so whatever's causing this problem isn't power and grounds going into this computer. So there is a possibility that the computer is faulty, no doubt about it. I mean, we got power and ground, the computer is dead. One might say, hey, let's throw a computer at it, right? Well, that computer is $1,500, and once you put it in the car, there's no taking it off. And I don't think at this point any of us are probably real comfortable putting a computer in this vehicle. Now, this vehicle does have a CAN bus operating system. We weren't able to communicate, but here we got CAN high, CAN low. And you can see it does go off, the other parts of the vehicle, these arrows, to other systems on the car. But here's our CAN high. It's a green wire with a white trace going to pin 17 at the ECU. Here's our CAN low. It's going to pin 16 in the ECU. And then also these same CAN high and CAN low can be measured at the throttle control module, pins 3 and 4. So maybe what we ought to do here is see if we do have communication on these wires. You know, obviously if the computer wasn't able to communicate, let's see if there's anything going on with the CAN bus system. So now we're diagnosing a wire that carries data. So we're going to be using a lab scope here, and we're just going to see if we got any kind of data going on here. Now there's lots of things that you can train your students on about, you know, a CAN bus system. I mean, there's more things about a CAN that I'd have to actually look up and read than I can truly remember. But there's a couple key points, I think, that if you were to memorize anything about a CAN bus system, there's a couple things we got to know. And this is true across the board, whether you're working on a Ford, Chrysler, Toyota, or whatever. But in a CAN bus system, there's going to be two what they call terminating resistors. So in this computer, in the ECU, there is a 120 ohm resistor across these two pins. And off somewhere else, could be the body control module, the instrument panel cluster, whatever, there would be another 120 ohm terminating resistor across CAN high and CAN low. So you kind of got a loop there with two 120 ohm resistors on either end. And then anytime there's a controller, they just plug those in parallel across these two lines to make a connection. Now the reason for those terminating resistors is kind of twofold. One, it does kind of load the circuit, so it keeps these wires clean. You know, you're not going to have inductive currents jumping on these wires with those two high resistance resistors on either side there. It's going to limit the ability for current to flow through these wires. So it has a filtering effect, and also it's useful for diagnostics. So we can measure resistance, and because they're kind of connected in parallel with each other, here again, your knowledge of Ohm's law. If we shut the key off here and we disconnect the battery, we should see around 60 ohm resistance across these two pins. But let's see if we got a signal here first. That's what we're trying to do. So I got my ground hooked up. We're going to turn our lab scope on. Right now, channel 1 is being displayed. That's the red lead. Channel 2 is the blue. We're going to need both channels for this. So we're going to turn channel 2 on. So here's our two channels, channel 1, channel 2. Just to help for clarity, just so you can kind of keep things straight, CAN high is 17, CAN low is 16. The sun is high in the sky and it's red hot orange, so we're going to put the red lead on 17. That's our CAN high. Oh, looky there, there's something going on there. And we're going to take the blue, is like the ocean, low to the ground. We'll put that's CAN low. And oh, looks like there's a signal coming in on both of those. And so if I zoom in here and I pause this, hey, it looks like we got a signal on CAN high and CAN low, or do we? And I can recall the first time I did this on a real car, I was kind of confused by what I was seeing. And so here's your tip. When you're viewing any kind of two-wire data bus where you're having a high and a low, don't look at the patterns spread apart like this, because that you might be looking at a ghost image on the other side. Remember that they are connected through these other controllers to each other. And so if there was an open or something like that, it could fool you into thinking that, hey, you got a pattern on both of these. So if we would I'll run this again. And now what I'm going to do, I'm going to bring this 0 line up with channel 1. So I'm going to bring that up, and let's see if we got indeed two separate patterns here. So I'm bring that up there. And look what we got here when I it is a single pattern. Pause that in just the right place here. There we go. There we go. So here's the other thing you to know about CAN bus. So our CAN, when the system is at rest, we should have around 2.5 volts. So if we count up from the 0 line, there's 1 volt, 1.5, 2, 2.5. So here's our arrest voltage. So when the modules aren't communicating, there's our 2.5 volts as top line. CAN low should be around 1.5 volts. It pulls it low. So there's 1 volt, there's 1.5. Here you can see our voltage per division. So we got a CAN low signal here, but CAN high should be at 3.5 volts. And so if we count that up, 1, 2, 3, 3.5, looky here, there's no CAN high voltage at all. So what we were looking
Darcy,
at there.
12:10. I'm sorry, Darcy. 12:10. 5 minutes. 5 minutes.
We got 5 minutes?
Yes,
Wow,
sir.
okay.
5 minutes left. Go ahead.
Okay.
You're good.
All right. So so we got a CAN high problem here. So let's go ahead and do some other tests here real quick. And let's go down to, we can check see if we have a pattern down here. So we'll put this on CAN low, this on CAN high, and start our scan up again. And look what we got here. Here we have a pattern. 1, 1.5, 2, 3, 3.5. So here we're getting the 3.5 volts here. So we weren't getting it on the power side, on the computer side, but we have our CAN bus over here. Let's look at our wiring diagram once more. So no CAN bus here. We are getting a CAN bus here, so that means that there can't be a problem with the terminating resistor and the other computer. There can't be a problem here with this wire or this wire because this is getting the signal. We are getting a CAN low signal on pin 16. We're just not getting a CAN high signal here at 17. So using a process of elimination, we must have a faulty wire between, really between here and here. There's got to be a faulty wire. So we can click on the wire and replace it. There's our brand new wire. And let's check and see what we got when we measure our CAN bus system over here. We'll run this again. If we have a pattern here now, then we know we've fixed our problem. So let's take a look here. Hey, look at that. There's our CAN high, there's our CAN low. So kind of in summary, when you're looking at these patterns, bring your 0 lines together, look for 1.5 volts on CAN low, a rest voltage of 2.5, and then your CAN high should be 3.5. There has to be a differential between the two of 2 volts or no message is relayed. So because we were only getting the CAN low voltage or signal into the ECU, it wasn't interpreting data being sent. There has to be this 2 volt differential. So I'm assuming now that the car is going to start and run, which it does. Look at that. Runs great. So in closing here, what we're going to do is put all our tools away, obviously. And we're going to hook up our computer back, okay? Make sure the car starts and runs. Perfect, okay? We'll go over here and grab our work order, and we would fill out our work order. That might take a good 20 minutes or so. Failure resolved, verified repairs, diagnose at work form. When I click this button here, everything's going to go away. Darn it, look here, we got in a hurry. Failure resolved, but there are other issues. There's stored fault codes. So from a student's perspective, what they're going to see is they're going to get a score for how they did. And they did nick us here a little bit for not clearing the codes. From the teacher's point of view, and this is what's really important when you're teaching from a distance, is this is what the teacher sees. They see the work order write-up, they see the invoice, and then here's the gravy right here. Every single diagnostic step we took to diagnose this fault. So if you're teaching from a distance, what would it tell you if the number one thing up here, instead of diagnostic tester opened, they replaced the CAN high wire? Well, nobody's that good. I mean, somebody either alerted them to the answer or whatever. But here we have hard evidence that the student actually did the work. When they, how much time they spent, how many sessions they did, first date, last access, everything is laid open there for you. So Thank you again for this, allowing me this opportunity. We'll open it up here for questions really quick, Mark. I know we're really short on time. I guess I got to let the time get away from me. So.
Yeah, that's okay. We're coming up on 12:15. I saw someone raised a hand. Let me see if I can figure out how to enable that part. I don't see it here, folks. If you don't mind quickly, you could put that question into the chat box. And please take the poll. That's a reminder. Take the poll and the survey, and reach out to us through John Mummert if you'd like, and we can get any additional questions answered. Unfortunately, with the time remaining, I've got to jump from this session and get another session started at 12:30 Eastern for Skill Vary, the virtual spray painting and welding. So I would have to say we need to close out the session at this time. Darcy, thank you very much. The Sim Master Sensei from Great Bend, Kansas, joining us today. So thanks again, Darcy. And thanks for
It's been my pleasure. I hope you all have a good rest of your day. So thank you again.
Everyone attending. We appreciate it. Have a great day. Oh, the key word. By the way, the key word today is candy. There goes Darcy, but please jot that down. The key word today is candy. I'll write that in there. There we go. Thank you, folks. Take care.